Okay, welcome back everybody to the last topic of the current unit. Today's topic is about two special right triangles. These are easily the two most important right triangles of your life. One is called the 45-45-90 triangle, and the other is called the 30-60-90 triangle. And especially if you go on past Algebra 2 in mathematics, these two are going to be critical to what you do in pre-calculus. Okay, so we got two theorems, and then we got some examples to go with each. And so let's get started. The first triangle that we'll look at is the 45-45-90 triangle, and the theorem that goes with that is relating the sides. And these are really kind of shortcuts to the Pythagorean theorem. You can figure out whatever you need with a Pythagorean theorem, but if you know some shortcuts, your work will get done quicker. Okay, so the first theorem says in a 45-45-90 triangle, the legs are congruent and the hypotenuse is the square root of 2 times a leg. So if you look at the triangle that I have drawn there, it's a 45-45-90. You can see by the angles. And we know from the converse of the isosceles triangle theorem that if two angles of a triangle are congruent, then the sides opposite those angles are congruent. So that shows you, and I have that marked in red there, that those two sides are congruent. And those are called the legs of the triangle. So the theorem we'll prove that here in our next screen. But that's what the theorem says. All right. So here's a proof. We already said that the legs were congruent, and so the other part of the theorem says that hypotenuse, which we're calling y in this diagram, is going to be square root of 2 times the leg, which we're calling x. So we just set up a Pythagorean equation there. You see it there, x squared plus x squared equals y squared. It's just a Pythagorean theorem applied to that triangle. Let's combine some like terms on the left side. So we got 2x squared on the left side is equal to y squared. And then on the third step there, I just switched sides of the equal sign there. So y squared equals 2x squared. On my fourth step down, just took the square root of both sides of the equation, so the square root of y squared on the left side and the square root of 2x squared on the right side. We know the square root of y squared is going to be y, so you see that. And on the left side, the square root of 2x squared is, you see that right there. And then on the next step down from there, we're going to break up that radical into two pieces. So the 2 goes under its own radical, and the x squared goes under its own radical. And then our second to last step, we're just going to bring down that y again and bring down that square root of 2, and then the square root of x squared is just going to be that x. So we get y equals the square root of 2 times x, and then if you kind of translate back into words, we're saying, looking at this diagram, that the hypotenuse, which we called y, is the square root of 2 times a leg. So that holds no matter what the sides of the 45-45-90 triangle are. Okay, so that's the proof of the first of our two theorems today. So let's take a look at an example that's going to use that. Here's why you want to know this theorem, because of its shortcut value. So the directions say find the value of x. So you see the 45-45-90 triangle there. You know one leg is 7, and of course you would know the other leg is 7 because the legs are congruent, but that's not what the question is asking. It says, what's the value of x? So what's the hypotenuse? We just saw when we proved the theorem that the hypotenuse in a 45-45-90 triangle is the square root of 2 times one of the legs. So all you have to do is put in a 7 there for the leg. So the hypotenuse, which is x, equals the square root of 2 times that leg, which is 7. And remember that when we deal with radicals, that comes after the number. So we're going to say that the hypotenuse x is 7 times the square root of 2. Okay, so that's all there is for that one. Let's do one more example with the 45-45-90 theorem. Okay, so here you see another 45-45-90 triangle, and we've got to find the value of x. So this time they know, I guess I didn't write that in there. I guess I'm supposed to say that, give that to you. Okay. This time we know that the hypotenuse is 3, but we don't know the legs. Again, you could solve that by the Pythagorean theorem, but you can also use your new shortcuts. So in this particular problem, we know from the theorem that the hypotenuse is the square root of 2 times a leg. Let's plug in the numbers that we know from the diagram. My hypotenuse is 3, equals the square root of 2 times the leg, which is x. I'm going to go ahead and switch sides there in that third step. I like to have that variable on the left side. So we got the square root of 2 times x equals 3. Now, of course, in that fourth step, I'm dividing both sides by square root of 2. So here's where we're at right there. X equals 3 divided by the square root of 2. Now, hopefully we remember from simplifying radicals, we are not allowed to have a radical in the denominator of a fraction. So what we do is called rationalizing the denominator. So we're going to take that 3 divided by radical 2 and multiply by square root of 2 over square root of 2. So that's equal to 1. So we're not really changing the fraction, we're just making it look different. So when you multiply by square root of 2 or square root of 2, the top of your fraction becomes 3 times the square root of 2, and the bottom is the square root of 2 times the square root of 2, which is the square root of 4, which then simplifies to 2. So there's your final answer right there. The square root of 2 times the square root of 2 is 2, and so there's your final answer for that leg of, and actually that's both legs, right, of that 45, 45, 90 triangle, since the legs are congruent. So there's your one shortcut theorem that you need to know, the 45, 45, 90 triangle theorem. Okay, so the other theorem that we need to know is called the 30, 60, 90 triangle, again named after the angles of the triangle. And so that theorem says this, in a 30, 60, 90 triangle, the length of the hypotenuse is 2 times the length of the shorter leg, and the length of the longer leg is square root of 3 times the shorter leg. So here the legs are not congruent like they were in the 45, 45, 90. So in a 30, 60, 90 triangle, the legs have different lengths. So what the theorem says, and then we're going to prove it, is the hypotenuse, which I called h here, is twice the shorter leg. So we know from the inequality in one triangle theorem that the shorter leg is opposite the smaller angle. So this x, the shorter leg, is opposite the 30-degree angle. And this y, which is the longer leg, is opposite the 60-degree angle. So again, the shorter leg is opposite the 30-degree angle, and the longer leg is opposite the 60-degree angle. That's the way it works as far as inequalities in one triangle. So this theorem is saying, and like I said, we're going to prove it, this theorem is saying that the hypotenuse, which we're calling h, is twice the shorter leg. So hypotenuse is 2 times x. That's what the theorem says. And also the longer leg, which I called y here, is the square root of 3 times the shorter leg, which we called x. So there's the two statements that we want to prove in our proof. And if you can remember those two shortcuts right there for this triangle, then these special right triangle is quicker to solve. Okay, so this proof is a little bit more involved. So let me start it out. We're going to start out with an equilateral triangle. So remember, an equilateral triangle has 3 congruent sides, and I just called them all 2x, and the reason I did that is to make the arithmetic easier. And so we know that when we have an equilateral triangle, it's also equiangular. That was one of our other theorems. So we know that all 3 angles are going to be 60. So I'm going to write that in there. That's 60 degrees. That's 60 degrees. And I'll get back to that angle Q in a minute. So what I'm going to do is I'm going to draw an altitude from point Q perpendicular to the opposite side. So an altitude of a triangle, we haven't really talked about it this year, but you probably know what it is. An altitude is how tall the triangle is. So an altitude of this triangle through point Q then is going to be perpendicular to the opposite side. So I'm going to draw a dotted line in here for that altitude. So this altitude from point Q perpendicular to the opposite side, so we have this, is going to form 2 triangles. And first I'm going to try to convince you that those 2 triangles, I'm going to call this point S right here, right there, that's that point down there. I'm going to convince you right now that those 2 triangles are congruent. First of all, they both have a hypotenuse which is congruent. They're right triangles, obviously. They both have a hypotenuse which is congruent. And this common side here is a leg. And so those 2 triangles are congruent by HL. Okay, so they're congruent by HL. And so that tells you that these 2 segments down here, PS and SR, are going to be congruent to each other by CP/CTC. Corresponding parts of congruent triangles are congruent. See, you can't forget that. And that means that since those 2 pieces there are congruent and they add up to 2x, then each one is going to be x. Each piece is going to be x. Okay, so the first part of our proof was that the hypotenuse is twice the shorter leg. Do you see it right there? I mean, there's your there's your hypotenuse right there. That's 2x. And there's your shorter leg. I should have gone back up here and remember I said I was going to go back to that third angle up there. So these two angles here made by the two triangles are going to both be congruent by that CP-CTC. So they're splitting 60 degrees and congruent. So those are both 30 up there. And so we have basically two congruent triangles, which are both 30, 60, 90 triangles. Okay, so back to what I was talking about. This hypotenuse here is 2x, and the shorter leg is 1x. And so you can see we just already proved that part of the theorem, that is the hypotenuse is equal to two times I'll call the shorter leg SL here, shorter leg. So the other part of the theorem is to compare the longer leg, which I'm going to call this Y here. The longer leg, which is Y, with the shorter leg, which is S. If you just look at that right triangle on the left. Okay, so we're going to set up a Pythagorean theorem just using this yellow triangle here. So set up a Pythagorean theorem. It's a right triangle, so we can use the Pythagorean theorem there, and we get x squared plus y squared. So leg squared plus leg squared equals hypotenuse squared. So that's a 2x. Going to be squared. All right, let's simplify that. And so we get x squared plus y squared equals 4x squared when I square out that 2x. We have like terms, so I got y squared equals 3x squared. All right, subtracted x squared from both sides. Now let's take the square root of both sides. So the square root of y squared equals the square root of 3x squared. So we know the left side, the square root of y squared, is just going to be y. And we can break up the right side into two separate radicals. So that's the square root of 3 times the square root of x squared. Simplify that. So you go y equals the square root of 3, square root of x squared. Of course, it's just going to be x. So if you look at what we just proved up here, because we already proved that one just by looking at the diagram, the hypotenuse is twice the shorter leg. But now if you look at y equals 3 times, y equals the square root of 3 times x, if you look at what we proved there, y is the longer leg. And so we can write that the longer leg equals the square root of 3 and that x with the shorter leg. So there's the proof of the 30, 60, 90 triangle theorem. Okay, let's do a couple examples on that, and then that's all you're going to need to know for this section. So here's a typical problem dealing with the 30, 60, 90 triangle theorem. Find the values of x and y. X is the shorter leg. Obviously, it's across from the 30-degree angle. Y is the longer leg. It's across from the 60-degree angle. So remember the theorem that the hypotenuse is twice the shorter leg. So in this case, the hypotenuse is 16. So x is 8, right? Because it's half of 16. So once you got the shorter leg, then it's easy to find the longer leg. Because remember, longer leg equals, from the theorem, square root of 3 times shorter leg. So you want the longer leg. That's the y across from the 60-degree angle. So y equals square root of 3. The shorter leg we already saw was x, which we said was 8. And so we're going to write that as y equals 8 radical 3, or y equals 8 times the square root of 3. So there you have it. There is your shorter leg, which was called x, and here is your longer leg, which is called y. Much better than the Pythagorean theorem as far as the time it takes you. All right, I have one more example here. So again, you see a 30, 60, 90 triangle, and same directions. They want us to find x and y. This one's a little bit tricky because they're giving you the longer leg, right? The longer leg is opposite the 60-degree angle. So if we can find the shorter leg, we're going to need to find the shorter leg first before we find the hypotenuse. Once we find the shorter leg, then we'll just double it to get the hypotenuse. That'll be easy. So the tricky part is getting that shorter leg. So all we're going to have to remember is, what is the relationship between the longer leg and the shorter leg? Well, if you read the theorem again, the longer leg equals the square root of 3 times a shorter leg. Okay, so let's put the longer leg in there. That's 11. So 11 equals square root of 3 times a shorter leg, which is x. I can turn this around just because I'm more comfortable that way. So square root of 3 times x equals 11. Let's solve that by x, or for x by dividing by radical 3. So that's going to give x equals 11 divided by radical 3. Okay, now recall that that's not a simplified radical because you have a radical in the denominator, which is not allowed. So we're going to rationalize the denominator. Rationalize the denominator by multiplying the top and bottom of that fraction by square root of 3 divided by square root of 3. In case you forgot your algebra, you're looking at that denominator. That is what gets multiplied by the top and bottom. Because remember, this is just another name for 1. So you're not changing the number, you're just making it look different. And so if we multiply straight across, we're going to have 11 radical 3 for the numerator. And remember that radical 3 times radical 3 is really radical 9, which is just 3. So we've successfully gotten rid of that radical in the denominator. So we got x, that's a shorter leg. And now remember, we just said if you want the hypotenuse, just recall from the theorem that the hypotenuse equals 2 times a shorter leg. So now it's easy. So that hypotenuse, which we called y, equals 2 times our fraction here. So 2 times 11 root 3 over 3. So that hypotenuse is y equals 22 root 3. Remember, you're multiplying those numbers outside the radical, not the number inside, over 3. Okay, so there you have it. That's solving using the 30-60-90 triangle theorem. All right, to summarize this and what you need to take away, and this is so important. I've got actually version 3 on here. I got version 1, version 2, and version 3 coming up. This is critical. We get kids in pre-calculus that do not know these triangles, and then they get lost, and it's hard. So let's learn these. Let's learn these shortcuts. Here they are. You got 2 special right triangles. One is the 45-45-90 triangle. The things you need to know about that are the 2 legs are congruent, so their measures are equal. And the hypotenuse of a 45-45-90 is whatever the leg is times radical 2. And the other takeaway from this lesson is the 30-60-90 triangle theorem. And it's a little bit more complicated. That type of triangle has a shorter leg and a longer leg and a hypotenuse. The shorter leg is opposite the 30-degree angle. The longer leg is opposite the 60-degree angle. Here's what you need to know. The hypotenuse of a 30-60-90 is twice the shorter leg. And the longer leg of a 30-60-90 triangle is square root of 3 times the shorter leg. If you can remember that and get that down and practice it with our 3 opportunities we're going to have, you're going to be ready to go. Okay, there you go. Let's get some practice. All right.